Statistical Rethinking, second edition, chapter 13. And we're just starting the hard questions. We're on 13H1. Okay. So if you're the first time you look at this, this is the question, and just its sheer size can be a little bit intimidating. But basically everything from here to here is just telling you something you need to do to the data in order to do this problem. Okay. So you can read that in your own time, and I will just execute what that first top part is telling us. Okay. Now, the basic idea here is that there is a survey of women in Bengali, and they're trying to assess how likely it is that women are using contraception across the different, districts in Bengali. So, where these people are living. The different districts where they are living within Bengali. Okay, and so what we are meant to do is to model the use of contraception by district. Okay, and so that's what we're going to do, and we're going to do it in two different ways. First, we're going to use a fixed effect model where each district basically gets its own beta coefficient, right? And then we will use a multi-level or a hierarchical model where we are kind of applying a hyperparameter to the effective district ID. All right. Yeah. So I think that is all we need to do. So then we're going to look at the difference in the model predictions and then try to understand those differences. Okay. So first we need to load the data. Well, speaking of that, so before you run any of this, you need to make sure that you have installed and loaded Stan and Rethinking, and you can do that with this whole top part of the code here. So anyway, back to the question. Here we are. Okay, so so we load the data, and the thing that all of this first top part is telling us to do is basically this one line right here. Okay, so we're creating a district ID for each district. Okay, so this is what we have. And so now we need to fit a fixed model and a hierarchical model to this. Okay, so that's what we're going to do. So I have my data, and all I have is contraception as well as the different districts. Okay. So my fixed model looks like this here. We're modeling this as a Bernoulli distribution. Okay. So I can do that with dbinom 1p. I think there's even a dburn function in the Rethinking package. I'm not sure about that though. So we use a logistic link function where we are just regressing on district, and then we need a prior for district here, and I've just taken this one out of the book, or what's common in the book. The way the hierarchical model differs, okay, it is so it's identical up until here, but now when we go to assign the prior for a district, we don't give it hard-coded values. Instead what we do, I usually like to keep it in our context. Instead what we do is assign priors to our prior for a district. Okay, so here, instead of d norm being a 0, 1.5 normal distribution, it is a d norm a dist bar a dist sigma distribution. And now we need priors for these what are called hyperparameters, and so that's what we have here. Okay, so you can kind of play around with these a little bit. Usually when I'm making these hierarchical models, from a fixed model, I will assign the hyperparameter for the mean to be the same as what the mean for the fixed parameter version, and then for the sigma, here it's 1.5, I will assign the corresponding a dist sigma 1 over that value there. Why 1 over? If I'm using an exponential distribution, because the mean of the exponential distribution is 1 over whatever you put in there. So 1 over 1.5 is 0.67. Okay, so we run this, I've already ran them, and I'm just hiding the output here. So now we need to, so we're going to plot the predictions of these models. So I'm extracting the posteriors, and this is what they look like here. Okay, um, and so uh, now I'm going to, well, let's look at the first model here. So we have 2,000 observations across 60 districts, and so I'm just going to take the column mean of each of these for each district. Okay, so that's that, and for each of those I'm applying the inverse logit function. Okay, so that's going to bring it back to the proportion scale or the probability scale for me. Okay, and then I also grabbed the, I'm going to plot the raw data as well, and so what I've done here is I've grabbed the how do I want to say this? The proportion of used contraception for each district. And so, so this is the code that I use to do that. It's an aggregate function. So you can run this and kind of play with exactly why this works. And I've also grabbed the number of observations for each district. Okay. All right. So now I go about plotting these. So first I'm going to plot the raw data. And so I'm plotting P raw against each unique district ID. Okay. And something else that I'm doing here is I am adjusting the size of the marker according to N raw, the number of observations. Okay. And I'm doing that for each marker, although as I'm thinking about it, maybe I shouldn't do that for each marker. Maybe I should just do it for the actual raw data. So let me fix that real quick. Okay, so there we go. Okay, and now I'm plotting the fixed model predictions as well as the hierarchical model predictions. And so let's come down here. And in fact, let me zoom in on this. Okay, so so let's start by comparing the raw data, which is these hollow black circles, to the predictions made by the fixed effects model, which is these filled orange dots. Okay. So first of all, this horizontal dotted line represents the mean of the raw data. Okay. So predictions that are closer to that constitute shrinkage. Okay. So you'll notice that the orange dots shrink the prediction compared to the raw value in every case, okay, to some extent, more or less. Or they stay the same, like right here, it's basically the same, etc. Okay. Now, so there is shrinkage with this fixed effect model, and why is that the case? Well, it's the case because there's a prior distribution, applied to these predictions, right? And so the prior, the prior is constraining what the model is going to predict. Well, now if we go on to compare to these purple X's, now the purple X's represent the predictions from the hierarchical model, right, which we should expect to have more constraint or to be more constraining. We see that that's in fact the case, right? So the purple X's in fact constrain or shrink more than the fixed effect model. Okay. So that's all interesting. Now, what else is a little bit interesting here is, remember, I've coded the size, the number of observations for each district by the size of the black hollow circle markers. Okay, and so what's interesting is the smaller the observation, generally, the more shrinkage that there is. Also, more extreme values are going to be shrunk more, so it gets and extreme values are going to have less observations, so it's a little bit difficult to disambiguate these. But large sample sizes, or many observations within a district, are going to shrink less. So, for example, we take this one here. So that this looks to be a rather large sample size for this district, and notice how little shrinkage is taking place. Let's see, it's a little bit hard to find a good example here. Okay, I think over here might be a good comparator, right? So now we have a smaller sample size, and now there is quite a bit more shrinkage taking place, right? And I would expect that this observation here and this observation here look to be about the same distance away from the mean value. So all else equal, you might expect similar shrinkage, but that isn't the case, and it's because of the difference in the sample size there for each place. Let's see, was there anything else that I wanted to talk about here? Oh, I know what I wanted to do. It might be interesting. To compare these two models, so let's do that. Okay, so I can do that with the compare function. If I leave off the argument, then it just uses WAIC. Otherwise, I'd need to specify the other way of doing this, which is PSIS. But this will be good enough for here. And so we see that the hierarchical model is doing a much better job of predicting out of sample or presumably predicting out of sample data. Okay, so I guess that will be it.